Hello, I'm Don Swartwout from CAS, and I am pleased and honored to have this opportunity to talk to you today about an issue that is very important for successful machine learning. That issue is the use of high-quality data. We'll illustrate that in this presentation by focusing on how it affects examples taken from the field of structure-activity relationship prediction. It is possible to learn many things about chemical structures, and specifically their likely activities from aspects of the structure. That is an important field primarily because in drug discovery, it's possible to save large amounts of time and money by making predictions that eliminate inappropriate candidates and highlight potentially good ones in using simply software and data rather than expensive laboratory testing or clinical trials. This can be done in several different ways. One is to learn from molecular fingerprints. Another is to learn directly from smile strings. And there are several others that are out of scope for this talk. Our primary focus is on the effect of data quality rather than the specific choice of a machine learning approach. So what are molecular fingerprints? Well, they are lists of structural features. Different types of fingerprints can capture different sets of features. There are several of those available. Morgan fingerprints, for example, have been around for over 50 years, if I remember correctly. ECFP4 are extended connectivity fingerprints. There are several versions of those. And CAS has a proprietary fingerprint that's used in several of our products and many of our internal artificial intelligence activities. So they'll be a good candidate for use in this talk. On the right-hand side, I've listed the part of the CAS fingerprint for one of my personal favorite substances, which is caffeine. The fingerprints typically consist of long binary vectors where 1 indicates the presence of a feature and a 0 indicates the absence of the feature. Here I've taken the sparse approach and listed the indexes that have non-zero values. Smile strings, on the other hand, stand for Simplified Molecular Input Line Entry System. They're another way of representing structures that has been around a long time. In this case, they were introduced in the 1980s. Again, we're using caffeine, one of my favorite substances. Its smile string is listed below. I should mention maybe that there are multiple smile strings for a given structure. There have been some attempts to define canonical smile strings with mixed success. For this purpose, we are not going to be dependent on having a smile string in a canonical form. Smiles, as you may know, are very widespread. Most chemical structure editors can read and write them, and most cheminformatics systems can also read and write them. So they're a very effective way of both communicating chemical structure information and they are useful in databases of chemistry information. One example of that is the CAS registry, which has more than 150 million high-quality smile strings. And by high-quality smile string, I mean actually two things. One, the software for converting the structure into smiles has been thoroughly tested, and the structures themselves are the result of CAS's structure curation activity, which, among other things, ensures that the structure is accurate. I've mentioned CAS and our data several times, so here is an overview of the data sets, at least major examples of the data sets that we currently offer and where they come from. On the left-hand side, you'll see a number of different types of data that we provide. Structures and structure activity relationship information are on the third and fourth lines on the far left. As you can see, they're part of a much larger space of information. One of the attractive things about all this data is that CAS's curation processes ensure that there are well-developed connections among the various data items in these data sets. The sources for that data are many and varied. We curate data from over 50,000 scientific journals and other types of documents. Our registry has over 250 million substances. As I mentioned before, over 150 million of those are small molecules that have aisle strings. The documents that we cover include over 50 languages, and also, as you know, chemistry is an important source of patents worldwide, and we cover information from 109 patent offices around the world. Those are impressive numbers. There's a lot of data there, but data is only valuable if useful insights can be extracted from it. So in this slide is meant to illustrate that, where we start with data on the far left. CAS's curation processes ensure that the information in those data sets are identified and connected. And then there are many different ways to do analysis on that data and reveal additional insights from the data. So something like machine learning to predict the activities of chemical structures is one of many types of such analysis. Okay, diving more deeply into the SAR prediction examples we're going to use in this talk. The molecular fingerprint approach is done, well, there are actually many ways to do that. Specifically, the one used here takes each possible feature that's recognized in CAS fingerprints, and those can be fed as that binary vector that I mentioned before can be fed as a feature vector into the machine learning library. Or another approach, which actually works equally well, is to take a string that I showed on the earlier slide, which lists the non-zero entries in the vector, and treat them as if they were words in a language, and compute an embedding from that string. TF-IDF, term frequency and inverse document frequency, is a very common way to map text into a vector, and we do that here. And then a model can be selected by an AutoML system, and we use one in particular. So it tries many different model structures, random forests, support vector machines, many different types of decision trees, and so on. And then focuses on the model structure that works the best. So for the fingerprint examples here, we will be looking at the models that the AutoML system thought did the best job on the problems we gave it. To learn directly from smile strings, the other examples we're going to use in this talk are an example of large language models. Now, smiles are languages. They have a vocabulary that consists of chemical element symbols, punctuation that indicates bonds, double bonds, stereo, and so on. We have, for this purpose, we trained a large language model from scratch on SMILE strings. And then for a particular target, to predict substances activity on that target, we used a fine-tuning process based on assay data for the target. When you do that, you rarely know in advance how much of training is going to be needed for effective fine-tuning. So in each case, we ran 20 epochs of fine-tuning, and we kept the result that yielded the best F1 score. So we've done this with a number of different targets. For purposes of this talk, I will use the two that are listed here. One is Ames mutagenicity. This is a test that as listed here, bacterial reverse mutation. And it's useful because it can provide an early warning of substances that might be carcinogens. The document listed there has much more detail and information about the Ames mutagenicity benchmark. Another one that we'll use in this talk is blood-brain barrier permeability. Permeability is important because it protects the brain from substances that may be useful in other parts of the body, but could be toxic to brain neurons. I took the blood-brain barrier permeability example from MoleculeNet, which you can find at the URL listed here. It's a collection of publicly available benchmarks that cover a variety of machine learning tasks related to chemistry and life science. So, as you know, and as I've already alluded to, machine learning is a highly data-intensive process. Machine learning is all about learning to recognize patterns in data. So naturally, the more examples of that data of interest, the more likely you are to see multiple repetitions of the patterns that you're hoping to learn. So in many cases, adding more data to the training of a machine learning model is a good thing, and allows the model to be more accurate. However, adding more data to the training set is not going to be helpful if the data is not of adequate quality. So here's an illustration using the Ames mutagenicity benchmark. So this dark blue bar shows the F1 that was achieved in the fingerprints case, using a data set of Ames mutagenicity data. 0.836 is certainly a reasonable initial training result. But now let's imagine that an additional assay, a small one, has become available. So we add the data from that assay to our training set, retrain the model, and we are disappointed to find that the F1 score has actually dropped by a little bit from 0.836 to 0.826. What's going on? Well, it may be that another data set becomes available, this from a larger assay. We add that to our training set, and the data drops even more. Now we're down to 0.803. So what is happening here? Well, those two additional sets of data were a simulated data quality issue. They have the labels indicating whether the mutagenicity test had shown positive or negative were wrong. Now, that can happen with assay data in many different ways. For example, if two assays could be conducted for the same target, for the same substances, but with different detection times, different solvents, different measurement equipment. And that can result in data that looks like it's going to be helpful, but in fact is not compatible with other data items in the training set. When I corrected those 2 additional assays worth to have the correct labels, then as expected, the model showed a greater accuracy. We're up to 0.847, which is a slight improvement. Now, you might wonder, well, is that something that's that affects the fingerprint approach, but not the large language model approach? Well, no, you see the same pattern happening with the large language model approach. Slightly different numbers. Note in this case, the fingerprints give a better result in all 4 cases than the large language model did. Well, so you might wonder, well, is the large language model more susceptible than the fingerprint approach? Here is a case. Oh, I'm sorry. I skipped one slide. You might wonder, well, you know, we were using the F1 score for the as an accuracy measurement. There are other accuracy measurements. You might wonder whether other accuracy measurements are going to show the same problem as F1, and yeah, typically they do. Here's what happens specifically to the ROC-OC, the receiver operating characteristic area under the curve measure, which has exactly the same shape as we saw for the F1. Now, moving on to another example, that here in the blood-brain barrier permeability case, that turns out to be a case in which the large language model gets better results than the fingerprints approach does. But the shape of the curves are very similar to what we saw before. Adding the inappropriate data, or inconsistent data, I should say, causes the accuracy to drop for the most part, and then when corrected, the numbers recover. I did want to mention one thing that shows up in this case. If you'll notice the difference between the initial set and the results after the first edition of that small assay, the F1 number for fingerprints actually improves slightly. And that can happen. There is a certain amount of randomness involved in training machine learning models, especially, for example, I guess I should say, in initializing the weights of a model. So it's possible that data quality problems can be masked, at least for a while, by the nature of machine learning and the randomness that's built into it. So just a warning to that every now and then, something that really should cause a drop in accuracy will sometimes not do that. On the ROC-OC measure, we see exactly the same issue as before, this time without the ambiguity related to adding the first assay, the additional assay that produced confusing results for the accuracy of the fingerprint approach. Now, in this case, all of them have the same pattern that we've been observing. So in summary, to emphasize again, machine learning is all about adapting to patterns in examples, which means that machine learning is data intensive, and the more high quality data that you can use to train a model, the happier you'll be with the results. We've also illustrated that there are extensive high-quality machine learning libraries available. The libraries that enable large language model training have been heavily used and scrutinized and tested and are good quality software. Similarly, the ones in the AutoML system that we use for the fingerprint case, and many of those algorithms that the AutoML system use come from well-exercised, well-tested libraries such as scikit-learn and XGBoost and so on. So there's a lot of high-quality machine learning code available, both open source and in commercial offerings. And in general, models trained with one of those high-quality machine learning libraries will do a good job of finding and coding patterns in the training data. However, if some of the training data is wrong, as we saw, or if some subsets of the training data are incompatible with each other, then the model will usually, we saw one small example, one small exception to this rule. But if some of the training data is wrong, or if some subsets of the training data are incompatible with each other, then the models will usually suffer. And two morals of this story are: one, use well-established ML libraries. If you're trying to accomplish practical results, that's the way to go. Of course, if you were a university researcher doing machine learning research, then you might need to use libraries that are not so well established. And second, if you spend most of your time and resources ensuring that you have high quality data, and then you feed that high quality data through a well-established machine learning library, it gives you the best chance of successful machine learning outcomes. So thank you for your time and attention today. I hope you find this conference interesting and worthwhile, and I'm looking forward to the next opportunity to speak with you.